Okay, so now that we've had a look at the forward Laplace transform of the second shift theorem, or we've really been using the second shift theorem in the forward direction, we now want to look at the second shift theorem in the reverse direction, so for inverse transforms. And what that will allow us to do is to solve another type of an inverse Laplace transform very easily. So let's go straight in. Now, the second shift theorem, as we've done before, states that the Laplace transform of u of t minus c dot f of t minus c equals e to the minus cs f of s, providing, of course, that the Laplace transform of f of t equals f of s. Now, we can say this in reverse. It may seem a little bit convoluted, but you'll see why it's important to do this in a second. So if we do this in reverse, we'll say that providing f of s is the Laplace transform of f of t, then e to the minus cs f of s will be the Laplace transform of u t minus c f of t minus c. And what you should see is that we're now starting to get into the inverse transform territory. Because if we have a function that looks like this, e to the minus cs f of s, we can immediately say, oh, well, that must be the forward transform of u t minus c f of t minus c. And if we take the inverse Laplace transform of this and the inverse Laplace transform of the Laplace transform of this, we're just going to be left with the function on the right-hand side and the inverse Laplace transform of the left-hand side. So if we take the Laplace inverse transform of e to the minus cs f of s, that's going to be equal to the inverse of this, which is just going to be the function. The inverse Laplace transform of a forward Laplace transform cancel each other out. So that's just going to be u t minus c f of t minus c. So, and obviously that's also providing, of course, that that f of s is the Laplace transform of f of t. So if we have any function as a form e to the minus cs and then something else, if f of s is the Laplace transform, we assume it's the Laplace transform of f of t, then we can work out what f of t is by taking the inverse Laplace transform just of that part there, take the inverse of that, and that will give us f of t. And the c will give us the shift. So we're now going to be able to find immediately the inverse Laplace transform of this combination, this product of functions. It's just going to be ut minus c being the shift, and the function f of t will just be the inverse of that part of the function. So let's have a go at an example. So let's say the question was find the inverse Laplace transform of e to the minus 4s on s squared. So it's nothing that we've seen so far, but if you look carefully, it's of the form of e to the minus cs and then something else, isn't it? So we can say that this is actually going to be, write it down in full, e to the minus 4s dot 1 on s squared. And since we know that the inverse Laplace transform of e to the minus cs f of s is ut minus c f of t minus c, we can therefore say that c, the shift here, is going to be 4, and f of s is going to be 1 on s squared, which implies f of t equals t. Yeah, because the forward transform of t is 1 on s squared. This is where your kind of forward Laplace transforms come in really, really important. That's why it's important to get quite good. And there's not that many of them, but just to get quite good at doing forward Laplace transforms so that you can easily recognize them in the inverse. Just a bit like the integration of differentiation. So, so we can say that this answer now is just going to be u t minus 4 and the function f of t minus c, well, the function is t, So that's just going to be t minus 4. And the reason why is because the function is just t and the shift is 4. And if we were to do the Laplace transform of that, we could check that we end up with e to the minus 4s on s squared. Okay, so let's have a look at another one here. So we've got the inverse Laplace transform of 6e to the minus 2s on s squared plus 4. So again, I always like to write things out. So it looks like a result of a second shift theorem. So we know that Laplace transform of u, t minus c, f of t minus c, equals e to the minus cs f of s, if Laplace transform of f of t equals f of s. Therefore, I can say that the inverse Laplace transform of e to the minus cs f of s equals u t minus c f of t minus c. So over here, let's just rewrite that in a little bit more friendly terms. We can say that's going to be 6e. It's not so friendly. Let's do e to the minus 2s. So we get it in this form, e to the minus 2s, and then f of s dot 6 on s squared plus 2 squared. Yeah? And now what I'd like to do is do Laplace of the inverse Laplace transform minus 1, e to the minus 2s dot 2 on s squared plus 2 squared. And that's going to be times by 3. So we can see that e to the minus 2s gives us the shift, which is 2. So this implies that c equals 2. And f of s equals 3 dot 2 on s squared plus 2 squared. Yeah, I'm just taking that component over here. When that implies f of t, the inverse of this, is going to be, remember this is an a on s squared plus a squared. Okay, so that's going to be a sine 2t times 3. Okay, because we've got a linear factor here of 3. So we can now say that the answer is going to be u t minus 2 times the function, which is going to be dot 3 sine 2 t, but remember there's a shift in the t, it's going to be t minus 2. So that's going to be the answer. Okay, let's have a look at another one. The inverse Laplace transform of 2e to the minus 5s on s cubed. So again, first thing to identify is that this is some kind of forward transform of the second shift theorem going on, because we've got it of some kind of form of e to the minus cs and something else. So whenever you see something of the form e to the minus cs and something else, it should indicate something to do with the second shift theorem. So again, you don't have to do this, but what I always do is write down the second shift theorem from first principles, or almost, well, the whole thing. U t minus c dot f of t minus c equals e to the minus cs f of s, obviously providing that f of t, the transform of f of t will give f of s. I want to bother writing that down as well. Therefore, I can say that the inverse Laplace transform of e to the minus cs f of s will give me the inverse Laplace transform of the Laplace transform of this, which just cancels out the transform, so it's going to be the function of u t minus c f of t minus c. Yeah? Now I can make a nice comparison. I can just write that a little bit more friendly. So I'm just going to get e to the minus 5s dot 2 on s cubed. And now I've got it in the form of e to the minus cs dot f of s. So this is going to imply the shift c is going to be 5, c is 5, and f of s equals 2 on s cubed. And that implies that f of t is going to be t to the 2, t squared, yeah? Because the Laplace transform of t to the n, remember, is going to be n factorial on s to the n plus 1. That was one of the first videos that we did. So we can see from this that the inverse is, so t to the 2 is going to be 2 factorial on s to the 2 plus 1 is 3, which is going to yield this. So I know that f of t equals t squared. I can now say then that the answer is going to be u of t minus c is 5, of the function is t squared, but there's a shift of c, t minus 5 squared. Okay, so let's have a look at another one. So we've got the inverse transform of 3e to the minus 2s on s squared minus 1. So again, immediately we can see e to the minus cs, so the form of the second shift theorem. So writing out the second shift theorem, the forward Laplace transform of u t minus c, f of t minus c equals e to the minus cs f of s, providing that the Laplace transform of f of t is f of s. I know I keep repeating myself, and you don't do it if you don't want to, but I think it's a really good idea to write down your theory, because the theorems, because it will number one, it will reinforce them in memory. You'll recognize them more, and it's also good for justifying your reasoning as well. So I think it's always good to write it down. And then what we can say, therefore, is that the inverse Laplace transform of e to the minus cs f of s is going to be u t minus c f of t minus c. Yeah? So let's put this into that kind of form. So we've got e to the minus 2s dot 3 on s squared minus 1 squared. So that implies that c equals 2 and f of s equals 3 on s squared minus 1 squared. And that implies that f of t equals, I'm going to cross the 3 out and put that 3 as a linear factor, and I'm going to put 1 on top. So we've got a on s squared minus a squared. So that's going to be shine t. It's going to be shine t with a linear factor of 3. Okay, so 3 shine t. Yeah. And that's going to be f of t, and we've got c, the shift is 2. So therefore we can say that the answer is going to be u of t minus 2 dot the function 3 shine t minus 2. Okay, now let's have a look at another one. So we've got an inverse Laplace transform of 5e to the minus s on s. So again, e to the minus cs. It's very annoying having to write this out every time, but I'm going to do it. ut minus c f of t minus c equals e to the minus cs f of s, providing that the Laplace of f of t is f of s. So therefore we can say that e to the minus cs f of s, well, the inverse transform of that is just going to be u t minus c f of t minus c. So I'm going to rewrite the question, the inverse Laplace transform of e to the minus 1s dot 5 on s. So I can immediately see that the shift is going to be 1. F of s is going to be 5 on s, and that's going to imply that f of t equals 5. Therefore, the answer is going to be u t minus 1 dot f of the function, t minus c. The function here is just 5. Okay, there's no t, so therefore there's no shift either. So that's going to be the function, u t minus 1 dot 5. You can also write that as 5 dot u t minus 1 as well. That's also okay. Okay, now let's have a look at another one here. So we've got the inverse Laplace transform of s, e to the minus s on 2 on s squared plus 2. So again, first things first, we've got an inverse transform, something of the form e to the minus cs. So plus of u t minus c, so always state the second theorem, f of t minus c equals e to the minus cs f of s. Therefore, the inverse transform of e to the minus cs f of s equals u t minus c f of t minus c. So I can now rewrite this e to the minus a half s dot s on s squared plus root 2 squared. Always get it in the square form and in the denominator, because then it makes the inverse transform much easier. So that's going to imply, obviously, that c equals a half, and f of s equals s on s squared plus root 2 squared, which implies that f of t equals, that's going to be the cosine root 2t, I believe. And c is a half, so we can say that the final answer is going to be u t minus a half dot cosine root 2 t minus a half. Okay, now let's have a look at a slightly more complicated example. So we've got the inverse Laplace transform of 3 on s minus 4e to the minus s on s squared plus 5e to the minus 2s on s squared. Now, initially, it doesn't look that difficult. It's just, remember, we can use the property of linearity with Laplace, just as we have before, with the second shift theorem. But there's a slightly added complication, which you might be able to pick up on. It's to do with when the functions start and stop, specifically with regard to Heaviside, which come into play here. So, the first thing we can do, with principle of linearity, is split this up into the inverse Laplace transform of 3 on s minus the inverse Laplace transform of this plus the inverse Laplace transform of this. So let's do that first. So we can say that the inverse Laplace transform of 3 on s equals, normally we would say 3, correct? But we can actually say 3 dot ut. Remember, that doesn't change anything, because when c is 0, or ut minus c, when c is 0, is really just the function, the unit step function, isn't it? When t equals 0, it turns on. And since Laplace is defined from positive infinity to 0, the dot ut won't change anything. But it clarifies where this function turns on, which is at 0. And that's important if you have other components in the expression that do not begin at 0. Now, that's when it's good to put things in terms of ut. So let's have a look at the inverse Laplace transform of e to the minus s dot 4 on s squared. Just looking at that, I can see that's going to be u of t minus 1 of the function dot 4 t minus 1. Is that right? Yeah, because remember, f of t is going to be t, or 4t rather, and since we've got the shift, it's going to have to, whenever you have t, you just replace the t with t minus the shift, which is t minus 1. And then we're going to have the inverse Laplace transform over here of e to the minus 2s dot 5 on s squared. And that's going to be equal to u t minus 2 dot 5t minus 2. Yeah, if you don't know where those came from, just look at the first part of the video, and I went through that in a lot of detail. So we can see here, if we just look at these forward functions now, we can say that the function is going to be 3 when t equals 0, up to the point when t equals 1. When t equals 1, you have another function that comes into play here, which is 4t minus 1. And then when we get to t equals 2, we're going to have another function that comes into play. It's going to turn on at t equals 2. So if we want to kind of sketch out what this function is going to look like, we have to consider the cumulative functions as they start to build up. So we can say when t, for t is between, when t is between 0 and 1, it's nice and straightforward. We can say that f of t equals 3. When t goes from 1 to 2, we now have f of t equals 3, because remember, this function is turned on now until infinity. It's permanently turned on after t equals 0. So it's going to be 3, but at t equals 1 and onwards, we're going to have another function of 4t minus 1, which equals 3 plus, no, hold on, because this is minus, remember. So it's going to be 3 minus 4t minus 1, which is going to be 3 minus 4t plus 4. So we can say that f of t equals 7 minus 4t. Okay, and that's going to be between 1 and 2. Between 0 and 1, it's going to be 3. And now let's consider for t, when t gets to 2. So when t is greater than 2, we now have f of t is going to be everything that came before, which is 7 minus 4t. And we're going to add that to the function that turns on, when t equals 2, which is just going to be 5t minus 10. So 5t minus 40 is going to be t minus 3. Okay? So if we were to do... Oh, sorry. Couldn't see that, could you? Sorry. Not looking at the screen. That's my problem. Right. So if we do like a very, very kind of quick sketch of t0, and that's going to be the function, between 0 and 1, it's going to be 3. And then between 1 and 2, it's going to be 7 minus 4t. And it's always a good idea to plug in fact, not a good idea, you must always plug in the values of t at the function breakpoints, because it's not necessarily guaranteed. It doesn't have to start. One function doesn't have to begin where another function starts. You can have discontinuities. And this is expressed in Laplace here. So we've got the next function between 1 and 2, which is going to be 7 minus 4t. When t equals 1, 7 minus 4 is 3. So here it does actually begin at 3. At 2, it's going to be 7 minus 8, which is minus 1. So it's going to go down to something like this, to minus 1. And then when t is greater than 2, we're going to be t minus 3 is going to be the description of the function. So when t equals 2, right, the function does, in fact, equal minus 1 at that point. So that's... Okay, we can put a point there. And then it's just going to be t minus 3, and then it's just going to continue kind of like that. And then we have it. Okay, now let's have a look at another question. So we've got the inverse Laplace transform of 2 on s plus 3e to the minus s on s squared minus 3e to the minus 3s on s squared. So by the principle of linearity, we can say that f of t equals the inverse Laplace transform of 2 on s plus the inverse Laplace transform of 3e to the minus s on s squared minus the inverse Laplace transform of 3e to the minus 3s on s squared. So the inverse Laplace transform of 2 on s equals 2 dot ut. The inverse Laplace transform of 3 to the minus s on s squared is going to be e to the minus s dot 3 on s squared. And that's going to be equal to u t minus 1 dot the function 3t minus 1. And then we've got the inverse Laplace transform of e to the minus 3s dot 3 on s squared. You get to a certain point of doing this when you just cannot be bothered to write out the whole second shift theorem, and then the inverse of the second shift theorem, and the implication of the inverse of the second shift theorem. So I'm just going to assume that this is fairly intuitive now. But look at the beginning bit of the video, it's not. So that's going to be u t minus 3 dot the function, which is going to be 3t minus 3. Yeah. So we can say, therefore, that for t is between 0 and 1, f of t equals 2. Between 1 and 3, f of t equals, now at this point, remember we've got the original function, which is 2, but we're also going to add to that the function that now turns on at t equals 1, which is this, which is 3t minus 3, which equals 3t minus 1. It's the function there, it's the function there. And then for t is greater than 3, f of t is going to be all the previous functions, which is now described by 3t minus 1, plus the function that gets turned on at ut minus 3, which is 3t minus 3. But remember, we have to subtract that. So it's going to be minus 3t plus 9, which equals 3t minus 3t, so the t's are going to cancel. Is that right? Yeah, 9 minus 1 is 8. Okay? So if we were to plot that, what f of t actually looks like. So I always like to do just a quick sketch to begin with. We've got t and f of t between 0, 1, 2 and 3 equals 2. Between 0 and 1. Between 1 and 3. So at 1 is going to be 3 minus 1, which is 2, is going to start over there. Remember, always check that for discontinuities. And then at 2, it's going to be 6 minus 1 is going to be 5. It's going to go up to 5. And then between 2 and, oopsie daisy, what have I done? 0 and 1 is 2. Between 1 and 3, oh, sorry about that. That should be there. Between 1 and 3, that's 5. And then, is that right? 3 times 9 minus 1 is 8. Wait a minute, what have I done wrong? 0 and 1 is 2. 3t minus 1. So when t equals 1, 3 minus 1 is 2, that's correct. And then at 3 should be, okay, sorry, that should be at 8. And then afterwards it's just going to stay like that. So if we were to draw that a little bit better, so we'd have 1, 2, 3. 2 between 0 and 1. And then at 3, it's going to go all the way up to 8. And then it's going to remain at 8. It's always nice to have some kind of sense of scale to the function, and that's f of t. So you can see how we worked out what the function looks like when you have functions that turn on and off at different points. And that's what the inverse Laplace transforms allows you to do with the second shift theorem. So you can see from there how we got a function that looks like this, which I think is quite nice.